problem. Analyze the portal frame shown in the figure by flexibility method. Draw bending moment and shear force diagram. So this is the loaded frame A, B, C, D. A, B, C, D. Now this frame is a sway frame because if you take the section, vertical section, on the left and right side of the section, if you see the forces, they are not same, and also the support at A and at support at D, they are not at the same level, they are at the different level. So there will be a horizontal sway in this frame. So this type of frame is a sway type frame. Okay. Now in this numerical, the member AB is loaded by a uniformly distributed load of 25 kilonewton meter, and the length of the member AB is 2 plus 2, that is 4. Okay, and the member BC is loaded with a point load of 50 kilonewton at the center, and it is at a distance of 1.5 meter from the P. The total length of member BC is 3 meter. Then the next vertical member CD, it is loaded with a point load of 40 kilonewton at a distance of 2 meter from support C and 1 meter from support D. So the total length of member CD is 3 meter, and the moment of inertia for the given frame is constant, that is ER. Okay. So as usual, our first step is to find out the degree of static indeterminacy. Now for that we have to see the support. At support A, there will be a 3 reaction, that is vertical reaction at A, then horizontal reaction at A, and the third will be the moment. So there will be a 3 reaction. Now same way, there will be again 3 reaction, again there will be a 3 reaction at D. Okay, and the third reaction will be the moment. Okay, so total reaction here will be 3 at support A and 3 at support D. So total reaction will be 6. Now we know what is the formula to find out the degree of static indeterminacy. It is R minus 3. Okay, here 3 equilibrium equation we are using, summation Fx, summation Fy, and moment. So total number of reactions are how much? 6 minus 3. Okay, so here degree of static indeterminacy will be equal to 3. Okay, now here we have already found out the degree of static indeterminacy is 3. Now here we have to consider the redundant forces. So here, and also we have to select the redundant in such a way that redundants are nothing but the unknowns. So we have to select in such a way that this frame will remain stable. So for that, if you remove the support at A, then this frame will not be stable. So for that, we are removing the support D. So when we remove the support D, there are 3 reactions are there. So one is horizontal reaction, another is vertical reaction, and third one is the moment. So here we'll consider our first unknown Q1 equal to vertical reaction at D, second unknown Q2 as the horizontal reaction at D, and our third unknown Q3 as the moment at D. So this is our Q matrix, Q1, Q2, Q3, whereas Q1 is VD, Q2 here it should be Q2, Q2 should be HD, and Q3 is the moment at D. Okay, so after finding out the static indeterminacy and selecting the redundant forces, the next step is to find out the displacement corresponding to redundant in original structure, that is dq. Now here we have considered support D as a redundant support, and there the 3 reactions. So at that support there is no spring support is provided, and also the sinking of support D is not given. So here the dq matrix dq1, dq2, and dq3, and as well as dq matrix, it will be equal to 0. Okay, so after finding out the first 2 steps, okay, the next step is the M diagram. In M diagram, we remove the support D. That means we have released the structure with load. We have released the structure. Release structure means we have made that structure statically determinant, and this diagram is called as EM diagram or release structure with load. Next, we have removed all the load, that is UDL as well as the point load. Okay, and our first unknown is the vertical reaction at D, that is Q1. So we apply Q1 equal to 1. That means you apply the unit force at D in vertical direction. Then figure number 3 is nothing but again the release structure. Our second unknown is horizontal reaction at D, that is Q2. There we have applied the horizontal unit force in horizontal direction. And the third unknown is nothing but the moment at D. So in figure number 4, we have released the structure, we have removed all the loads, and at D we have given the unit moment. We apply the unit moment, that is Q3 equal to 1. So in this all these 4 figures we are going to find out the bending moment. Okay. Now next step, as we know, the displacement analysis of a release structure. Okay. Now here, now we know the what are the different columns of this table. Also we know the sign convention: hogging negative, sagging positive. So first zone we'll consider, that is TF. We'll measure the X from D point. Okay. Now on this side there is no any other force is there, so the bending moment will be equal to 0. So limit here D F. For D the length is 0 and for F it is 1, because we are starting from D, so the length of D is 0 and F is 1. Okay. Now next we are taking section in FC. Okay. In zone FC, measuring X from where? From D point. Okay. Now here there is a force of 40 kilonewton. It will act like this. We are standing inside the frame, and the nature of bending moment will be hogging. The nature of bending moment will be hogging. Okay. So here it is minus. So the intensity of force is 40 and distance. That means here you have to find out this much distance. Okay. So this distance will be equal to how much? This distance will be X minus this much distance. So X minus 1. So bending moment in zone FC, it is minus 40 into X minus 1. By solving this, we will get this equation. Okay. Now next we will take the section in portion CE. Measure X from C point. Now here origin is what? C. Okay. Now here, so what are the forces? Now this 40 will act like this. Again the nature of bending moment will be hogging. So again minus. But here for 40 this distance is completed at C. So here 40 intensity of the point load will be multiplied by the length, that is 2. So here minus 40 because nature of bending moment is hogging. So 40 intensity of force and 2 is the distance. So minus 80 will be the bending moment in portion C. Now the next portion that we are considering is EB. Measuring X from C point. Okay. Now here the first force, that will be the 40. Okay. So then it will act like this. So the nature will be hogging. Again minus 40 intensity of force into 2 is the distance. Okay, this distance is 2. Okay. Now the next force is the 50 kilonewton. This 50 kilonewton will act like this. Okay. Again the nature of bending moment will be sagging. We are standing inside the frame. Okay. So as the nature of bending moment is sagging, here the sign is minus. Intensity of force is 50. So here we have to find out this distance. So this distance will be nothing but it is equal to, so here total distance is x minus 1.5. Okay, x minus 1.5. So the bending moment in zone EB will be minus 50x in minus x after solving this expression. Okay. Now next, taking the section in region AB. Okay, this is the section XX. Measuring X from where? Now here X is measured from B now. X is measured from B. Okay. Now here first force now here it is very important now. Okay. Now here first force is minus 40 now. Now here 40. Okay. So it will act like this. Now instead of this 40 acting here, according to the principle of transitivity, if you act this force here, it will act here. Okay, so the nature of bending moment will be what? Yes, so the nature of bending moment will be here, it is hogging. Okay, so minus 40 x minus 2, because we are measuring from BB, so x minus 2. So for 50 it will act like this. Again the nature of bending moment will be hogging, so minus 50 into 1.5. so here at B this distance is completed, so 50 into 1.5. okay, now sorry, yes, 50 into 1.5, and this UDL will act like this. Again the nature is hogging, so here the value is minus 25 into the distance is x into x by 2. So if we solve this, we'll get this expression. Okay, so this was the bending moment for the bending moment for the release structure with load. Now we'll find out the next, that is value of M1 for the release structure with Q1 equal to 1. Again the first we'll take the section here, measure x from where? We'll measure x from D point, but this force will pass through this point, so this value for DF, zone DF, will be 0. Next we'll take in FC, again we'll measure x from where? We'll measure x from D point now. Okay, here also it is passing through this same point, so here also the value of bending moment is 0. Okay, now we'll take the section in portion EC. Here we are taking the section, measure x from where? C point. Okay, so this force will act like this, so it will be what? So 1 into x, that is x. Okay, so the nature of bending moment will be sagging, we are standing inside the frame, so plus, so it is x plus here. Okay, now if you take the zone in the next portion, that is EB, measure x from where? Measure x from C point. Okay, again this force will act like this. Again the nature of bending moment will be sagging, again plus, and this distance is x, so 1 into x is x. Okay, now next we will take the section. Okay, we'll take the section here, measure x from where? B point, measure it from B point. Okay, now this force will act like this. Okay, it will act like this. So nature of bending moment will be what? Hogging, sorry, sagging. So plus, now here this distance is completed up to B, that means B or C, it is 3. 2 plus 1, 3. So here it is multiplied. So 1 into 3 is 3. So value of bending moment for zone BA is 3. Okay. Next we will find out the bending moment for the release structure with Q2 equal to 1. Okay. Now here first we take the section in FD. Okay, measure x from D point, so it will act like this. So the nature of bending moment will be, we are standing inside, so the nature of bending moment is sagging, positive. So 1 multiplied by x, so it is x. Okay, now next we'll take the section in FC, measure x from where? D point. Okay, and the force will act like this. So again the nature of bending moment will be sagging. So 1 multiplied by the distance x, it will be x. Okay. Now next we'll take the section in portion EC, measure x from where? C point. Okay. Now this force will act like this. The nature of bending moment will be sagging. So plus. So here this distance CD is complete now. Okay, so here 1 multiplied by this distance, that is 3. So 1 into 3, it is 3. So here plus sign, because nature of bending moment is sagging. Now next we will take the section in portion EB, measure x from C point. Again here this force will act like this. the nature of bending moment will be sagging. So plus, so 1 is the intensity of force multiplied by the distance 3. So 1 into 3 is 3. Okay. Now this is important. Here we have written -1. Okay. So here, if we apply this, if we take the section here now, okay, then this portion, and if you measure the x from B point, now here instead of this force acting here, if you add this force over here, okay, the same line, okay. So due to this force, it will act like this, okay. So here the nature of bending moment will be what? Hogging. We are standing inside the frame, okay. So this force will act like this. This force is in this line, okay. So here we are standing inside the frame. So here what will be the nature of bending moment? It will be hogging, minus. So here we have taken minus. What is the intensity of force? Minus is 1. And this distance we have to find out here. Now we have to calculate this distance. Now this distance, I will take different, okay. So we have to find out this distance. So this distance is equal to how much? So total distance is x minus this much distance, that is 3. So here -1 into x minus 3. Okay. So here the bending moment in zone BA is -1 into x minus 3. So this became 3 minus x. Okay. So the limit we know that. For example, here I have written BA. Now for BA, what is the length? BA here it is a starting, so 0, and at A the length will be 2 plus 1 plus 1, that is 4. For EB here the length is what? 1.5, and for B the length is 3. Okay. So this was the bending moment for the release structure with Q2 equal to 1. Now we'll find out the bending moment due to Q3 equal to 1. Now here it is a moment now, so only you have to consider the moment, don't multiply by the length. So first in the zone FD, measure x from D point. So here the nature will be what? Sagging. Okay. So plus, we are standing inside the frame. Now in the next zone is what? The next zone is FC. Again measure x from where? Measure x from D point. Okay. Here due to this force, this nature will be again sagging. Okay. So again plus. So the intensity of this movement is 1. So only 1. We here multiply over here by the line. So we'll consider the next zone, that is C. Again x is measured from C point here. This movement will act like this. So the nature of bending movement will again sagging. So plus again 1. For EB also it will be the same. Okay. Again 1. Now for BA, if you take the section here now and measure x from B point, okay, so this movement will act in this way, okay. Or if you are not getting, instead of here, suppose at this point the movement is acting, okay, and that movement is acting like this, okay, here. So due to this movement, here there will be a sagging movement, okay. So as there is sagging movement, so their value is what? Plus, and for movement we do not multiply by the length. So here only the intensity of movement is 1, okay, and here we are measuring x from where? B point. So here the limit is 0 to 4, okay. So in this way we have found out the bending moment in the release structure. Now after that we are going to find out dQL1. We know the expression for dQL, integration 0 to L m into m1 upon EI. So here multiply m into m1. Okay. So here for first two zone, as the values of m1 is 0, so here this term will become 0. For CA the limit is 0 to 1.5 into minus 80 into x. So for EB it is limit 1.5 to 3. minus 50x minus 5 into x, and for BA limit 0 to 4 minus 12.5 x square plus 40x minus 155 into 3. After solving this, we'll get the value of dqL1 equal to minus 2200.625 upon EI. Okay. So after calculating dqL1, we'll calculate dqL2. Okay. Again, for zone DF limit is 0 to, for zone DF, as the value of capital M is 0, so this term will be equal to 0, and for FC limit 1 to 3 minus 40x into x upon EI. Then for second 0 to 1.5 limits for zone CE minus 80 into 3. Then for the next zone BA limit is for the zone EB limit 1.5 to 3 minus 50x minus 5 into 3, and the last zone, that is BA, limit 0 to 4 minus 12.5 x square plus 40x minus 155 into 3 minus x. After solving this, we'll get the value of dqL2. Okay. Now after finding out the value of dqL2, we'll find out the value of dqL3. Okay. Now here the value of M3 is 1. So for FC, the limit is 1 to 3 minus 40x plus 40 into 1 upon EI. Then for C, limit 0 to 1.5 minus 80 into 1 upon EI. Then for EB, it is minus 50x minus 5 into 1 upon EI, limit 1.5 to 3. And for BA, integration 0 to 4, then value of M is minus 12.5 x square plus 40x minus 155 into 1 upon EI. So after solving this integration, we'll get the value of dqL3 as minus 942.92 upon EI. So this is the value of dqL3. So after calculating the value of dqL1, dqL2 and dqL3, putting it dqL matrix, okay, so we'll get the dqL matrix. Okay. Now next in this video we'll first going to find out the flexibility coefficient. Okay, so flexibility coefficients. So here first coefficient is F11. So the formula is integration 0 to L M1 into M1 upon EI into dx. So here F11 means M1 into M1. So here whatever the values are there in M1 column, that you have to multiply by the M1 only. So here for the first zone DF, here value of M1 is 0. For FC again the value is 0. So this, for these two terms zone, the value will be 0. Then for C, the limit is 0 to 1.5. So x into x upon EI, plus for EB again limit is 1.5 to 3. Again x into x. And for BA, the limit is 0 to 4, 3 into 3 upon EI into dx. And if you solve this integration on the calculator, we'll get this value. And the final value of F11 is 45 upon EI. So this is the value of F11. In the same way, you have to find out the value of F12. You have to find out the value of F12 and F21. So here, what should be the value of small m? It is M1 into M2 or M2 into M1. Both will be the same. So integration 0 to L M1 into M2 upon EI into dx. So here again for first two zone, the value of M1 is 0. So we have to start from the zone C. So integration 0 to 1.5. So M1 is x, M2 is 3. So 3 into x upon EI plus integration 1.5 to 3, 3 into x. Then integration 0 to 4, 3 into 3 minus 6 upon EI into dx. So we are multiplying M1 into M. Okay. So after putting the values in this formula, you have to solve this integration and you will get this value. So final value of F12 equal to F21 is equal to 25.5 upon EI. Okay. So this is the value of second flexibility coefficient, that is F12 equal to F21. Okay. Okay. The next is F13 equal to F31. So here M1 should be multiplied by M3 or M3 should be multiplied by M1. Both will be same. So M1 for first two zone, value of M1 is 0. So for that term the values will be 0. So for C, integration 0 to 1.5, here value is x, for M3 value is 1. So x into 1. Then integration 1.5 to 3, again here value is x, here value is 1, x into 1 upon EI. Then for zone BA, the limit is 0 to 4, value of M1 is 3 and value of M3 is 1. So 3 into 1 upon EI. After solving this integration, we will get this value. So here the value of F13 equal to F31 is equal to 16.5 upon EI. Okay. So in this way we have found out the 3 coefficient. Okay. So the next coefficient is F22. So here as it is F22, so here M2 should be multiplied by M2. Okay, so F22 equal to integration 0 to L M2 into M2 upon EI into dx. So M2 column will be multiplied by M2 column here only. So first for first zone DF, the limit is 0 to 1, x multiplied by x. Then for next zone FC, the limit is 1 to 3, x multiplied by x upon EI. Then for next zone CE, limit is 0 to 1.5, 3 multiplied by 3. Then for zone AB, limit is 1.5 to 3, 3 multiplied by 3 upon EI into dx. So next zone is BA, limit is 0 to 4, 3 minus x multiplied by 3 minus x upon EI. Okay, so we have put the values of M2 in the above formula. Okay, here for all the zone, the value of EI is constant. After solving this integration, we'll get this value, and finally we'll get the value of F22, that is 45.33 upon EI. Okay, after calculating F22, we'll calculate F23. So the formula for F22 is F23 equal to F32 equal to integration 0 to L M2 into M2 upon EI into dx. Now here M2 row, here should be 3. So instead of 2, here there should be 3. Okay, so here because 2 into 3 it should be, so M2 into M3 upon EI. So here M2 column will be multiplied by M3. So here what is the first zone? DF, integration 0 to 1, x into 1 upon EI into dx. Okay, so next zone is FC, limit is 1 to 3, so x into 1 upon EI into dx. So next zone is C, limit 0 to 1.5, 3 into 1 upon EI into dx. So the next zone is AB, 1.5 to 3. Okay, 1.5 to 3. So 3 into 1. Okay, 3 into 1 upon EI. And last zone is BA, limit is 0 to 4. Okay, so 3 minus x into 1 upon EI. Okay, so after solving this integration, we'll get this value. And final value of F23 equal to F32 is 17.5 upon EI. Okay. Then the last flexibility coefficient is F33. Okay. So here we have to multiply M3 by M3. So all the values of M3 is 1. Okay. So here for first zone DF, limit is 0 to 1. So 1 multiplied by 1 upon EI into dx. For zone FC, limit is 1 to 3, 1 multiplied by 1 upon EI into dx. Next zone is C, limit is 0 to 1.5, 1 into 1 upon EI into dx, plus next limit is 1.5 to 3, 1 into 1 upon EI into dx, and last zone is BA, where the limit is 0 to 4, 1 into 1 upon EI into dx. So solve this integration on calculator and we will get this value. So the final value of F33 is equal to 10 upon EI. Okay. Now we have found out the flexibility coefficient, that is F11, F22, F33, F21, F22, F23, F31, F32 and F33. Put these values in this flexibility matrix, and this is the flexibility matrix for the given problem. Okay. Now after calculating flexibility matrix, you have to put the value of dq, then dql, then f and q in this flexibility equation or the equilibrium equation. So here DQ matrix is 0, 0, 0. DKL matrix minus 2200.625 minus 1588.75 minus 942.92 plus EF matrix is 1 upon EF 45, 25.5, 16.5, then 25.5, 45.33, 17.5, 16.5, 17.5 and 10, and Q1, Q2, Q3 are the unknown. Now here we will take EI common and we multiply on the other side, so the EI will get cancelled. We will take the DKL matrix on the other side. Okay. Then now here you have to multiply these two matrix. So here you have to multiply row by the column. So 45 into Q1 plus 25.5 into Q2, 16.5 into Q3. Here we have written equal to what? This 2200.625. Now second row 25.5 into Q1, 45.33 into Q2, 17.5 into Q3 equal to 1588.75. Now next 16.5 into Q1 plus 17.5 into Q2 plus 10 into Q3 equal to 942.92. Okay. Now here we'll get these three simultaneous equation. Solving this equation 1, 2 and 3, we'll get the three unknown, that is vertical reaction at D, which is Q1, horizontal reaction at D, that is Q2, and moment at D, that is Q3. And these are the values. Okay, so these are the values. Now these were the redundant values we have considered in the first case. Redundant means these were the unknown that we have considered. Now after finding out this unknown, now this structure has become statically determinate. Okay, now we have to find out the other unknowns in the problem. Okay, now first, as here at the support D, we know the vertical reaction at D, horizontal reaction at D, and also we know the moment at D. Now all these three values are known, so we can find out horizontal reaction at C, vertical reaction at C. Okay, we can find vertical reaction at C, horizontal reaction at C, and also we can find out moment in member CD. Okay, now here to find out this unknown, we have to use the equilibrium condition. So we'll apply the first equilibrium condition, that is moment at C equal to 0. Okay, consider anti-clockwise positive, clockwise negative. So here the MDC, that is which is acting in anti-clockwise direction, MDC, it is acting in anti-clockwise direction. Okay, so 25.48 plus, then 4.3, it is acting in which direction? Anti-clockwise direction again, so plus 4.34 into 3. Okay, then the 40 is acting in clockwise direction, so minus 40 into 2 plus MCD, it is acting in anti-clockwise direction, so plus. So here the value of MCD is what? After solving this, we'll get value of MCD 41.5. Okay, now we have to find out the horizontal reaction. Here it should be C, horizontal reaction at C. Okay, so for that we'll apply the equilibrium equation, summation of x equal to 0. Towards right positive, towards left negative. So HD, here it is acting towards right positive, so 4.34, SC is also acting towards right, and minus 40. And if you solve this, we'll get the value of horizontal reaction at C as 35.66. Okay, so after finding out the values at joint C, we'll find out the value, unknown value at joint B now. Now for that again we'll consider moment at B. We'll consider moment at B equal to 0. Consider clockwise negative, anti-clockwise positive. Okay, and where we are taking moment at B equal to 0. So first for this is point load. The point load is acting like this. So it is acting in clockwise, minus the distance is 1.5. Then MBC how it is acting? Clockwise. Okay, it is acting clockwise. So here it should be minus. It should be minus. Okay. Then 41.5 This 41.5, it is acting like this. It is acting in anti-clockwise. Okay. Sorry. Here MBC is this. It is acting anti-clockwise, so it is positive. And 41.5, it is MCB. It is acting in clockwise, so minus. Then 37.5 is vertical reaction at C. It is acting in anti-clockwise direction, so plus into the distance is 3. And if we solve this, we'll get the value of MBC. Okay, here we have found out the value of MBC 5. Okay, after that we have to find out the vertical reaction at B. Okay, so for that we'll apply the equilibrium equation, that is summation Fy equal to 0. So here 50 is the vertical force acting downward, okay, equal to VB plus VC. Now here we know the value of VC, that is 37.10. Okay, so 50 minus 37.10, we get the vertical reaction at B, that is 12.9. After finding the value at support B, then we'll find out here horizontal reaction at B is equal to horizontal reaction at C. So HB will be equal to 35.66. Okay, so after finding out the values at support B, okay, the next step is, okay, we'll find out the values at support E. Okay, so for that we'll apply the equilibrium equation, that is moment at A equal to 0. Okay, so where we are taking the moment at A, at this point we are taking the moment. Okay, so now force minus 5.2. So what is minus 5.2? This movement in member MBA. Now here this movement here, it is acting in anti-clockwise direction. So for MBA it should act in clockwise direction. It should be equal and opposite. Okay, then and then only the joint B will be in equilibrium. So minus 5.2 plus MAB. MAB is this movement acting in what? Anti-clockwise direction, positive. Then this UDL. Okay, so this UDL will act like this. It will act in clockwise direction. So minus 25 into length is 4. This will be the force, and the distance is what? 4 divided by 2, that is 2. Then 35.66. Here HB is what? Towards the right. Now for BA it should be towards left. Here it should be equal and opposite. So 35.66 into length is what? 4. So if we solve this, we'll get the moment in member AB as 62.56 kilonewton meter. After that, we'll find out the horizontal reaction at A. For that, we are applying the equilibrium equation, summation Fx equal to 0. So HA plus HB will be equal to the force, that is 25 into 4. So here we know the value of HB, 35.66. So 100 minus 35.66, we'll get the horizontal reaction at A is what? 64.34. And here vertical reaction at A will be what? That is equal to vertical reaction at B, that is 12.9. Okay, here it is equal and opposite. For that you can use the equilibrium equation, summation Fy equal to 0. Okay, now here first we have by using the flexibility method, we have find out the unknown at support D. Okay, then by knowing the values at support D, then we have find out the unknown at joint C. Then after finding out unknown at joint C, we have find out unknown at joint B, and then we have find out unknown at joint E. So in this way we have calculated the unknowns in the undeterminate structure. So after finding out support reaction, movement, the next step, that is the output. What is the output here? To draw the shear force and bending moment diagram. Okay, so first we'll draw the shear force diagram. We know what is the horizontal reaction at A, 64.34. okay, so in which direction it is towards the left. So 64.34. now in the member AB, it is loaded by what? UDL. So 25 kilonewton meter, okay, into 4 length 100. So 64.34 minus 100, the value we will get is 35.66. Okay, so here as it is a UDL, so you have to join this by a straight line. So here the value is minus, so it is on the right side of the B. Okay, then vertical reaction at B is what? 12.9. so acting upward. Then in this portion, in B portion there is no load, so we have to join by horizontal line. Here value is 12.9. So here there is a point load of 50 kilonewton acting downward. So 12.9 minus 50. So we'll get value what? 37.10. Okay. In this portion no load, again 37.10. And at C, what is the reaction? It is 37.10. Okay. Now horizontal reaction at C is what? 35.66. Okay, it is plus means it is towards right. Okay. Now in portion CF there is no load, so here the value is the same. You have to join by horizontal line 35.66. Here is a point load of 40. It is towards the left, so 35.66 minus 40. So we'll get what value? 4.34. Okay. In FD there is no load, so you have to join by a horizontal line. So here the value is 4.34 and vertical reaction at D is what? 4.34 acting towards right, because here it is plus. So at D value will be 0. So this is the shear force diagram for the given frame. So after drawing the shear force diagram, the last step is to draw the bending moment diagram. Okay. Now for bending moment diagram, already we have calculated the moment in member AB, BA and the respective members of the given frame. Okay, moment in member AB is what now here? It is 62.66. We know the sign convention, anti-clockwise plus, okay, and clockwise is minus. Okay, so here moment in member AB is what? 62.56. It is plus, plus means anti-clockwise. So I will keep the pane nearer to support A towards B on line AB. And I will rotate the joint in what? Anti-clockwise direction. Now I will rotate the joint A in anti-clockwise direction and it should cut the member AB once. Okay. So here the value 62.56 is on the left hand side of the support A. Okay. So here we are seeing. So you have to join this straight line. Then moment in member BA is what now? It is minus. Minus means you have to rotate the joint B in clockwise direction. Keep the pane nearer to support B towards A. And rotate the joint B in clockwise direction and it should cut the member BA once. So here this value 5.2 is on the left hand side of the B. So join this by a straight line. Then in member BC now, in member BC the moment is what? 5.2. So it is plus. That means here I will rotate the joint B how? In anti-clockwise direction. So I will rotate the joint B in anti-clockwise direction and it should cut the members once. So here the value 5.0 is above the line BC. Now here the moment in member CB is what? Minus. Minus means you have to rotate the joint C in clockwise direction. So I will rotate the joint C in clockwise direction and it should cut the line CB once. So here this is value 41.5. Okay. Now next, the force, the moment in member CD is what? Is 41.5 plus. So rotate the joint C in anti-clockwise direction and cut the member CD once. Okay. Then member DC. Here the value is what? Plus. Plus means you have to rotate the joint D in anti-clockwise direction. So I will rotate the joint D in anti-clockwise direction and it should cut the member DC once. Okay, so the value 25.48 is on the left hand side. So join this by a straight line. Okay. So here we have found out the fixed bending moment. Now we'll draw the free bending moment diagram. Okay. So these signs are very important to draw the bending moment diagram. So here in portion AB, which type of load is there? There is the UDL is there. For UDL, the value of free bending moment is WL square by 8. Okay. WL square by 8. Okay. So value of W is 25, value of L is 4. And if we solve this, we'll get the value of free bending moment is 50. So here as there is UDL, so you have to join this by a second degree curve. Okay. So this is the second degree curve. So value of the free bending moment is 50. Now in portion BC, there is a point load and that point load is acting at the center. So value is WL by 4. So value of W is 50, L is 3. So 50 into 3 upon 4. So the value is 37.5. Okay. Now next, here there is a point load, but the point load is not at the center. So value of free bending moment is what? WAB upon L. Now this is value of A and this is value of B. Value of A is what here? 2. Value of B is 1. So 40 into 2 into 1 and total length is how much? This much. That is 3. Okay. So we'll get the value 26.6. So join this by a straight line. So here we have imposed the free bending moment diagram on the fixed bending moment diagram. So this diagram is a superimposed bending moment diagram. In exam they will told to draw the bending moment diagram. So there you have to draw the superimposed bending moment diagram. Okay. So thank you for watching this video.